ask a question now.
Alexei, what is the rate of convergence? That was what I read.
Yep.
What is the rate of convergence of what? With what parameter?
Yes, thank you. Thank you for the interesting talk. What is the rate of convergence of these oscillating integrals with respect to this Gaussian parameter?
Yes. The Gaussian parameter, if you're dealing with this rate of convergence as a numerical question, as I said, if you're dealing with numerical methods with a fixed precision, as eta tends to 0, you're going to find that your finite word length calculations become inaccurate as eta gets smaller and smaller. So your results become, as in the technique of Wave summation, if you're using this as a numerical method, you want to be able to find a plateau of stability, and the stability of the plateau tells you the number of decimals you can expect to be correct in your answer. If you're dealing with it analytically, the analytic numerical results can be used just to verify that the analytic result is valid. Okay, but you can't, as I said when I dealt with the illustrative example at the beginning, you can't take eta too small unless you increase the word length of the calculation on the computer you're dealing with. These days, there are sets of functions. There are methods for dealing with multiple precision architectures and calculations, and so you can go a lot further than is the case with normal fixed word length double, triple, or quad length calculations. But there will, if you've got a fixed word length, then there'll always be a limit where the method is going to blow up if you're using it numerically. Does that answer your question?
Yeah, okay, thank you very much.
Any more questions?
I would actually like to make a comment.
Yes, David.
It starts from some generalities, and then I will get down to a little more specifics. First of all, it's very useful to keep in mind that physical fields never diverge. They're always finite. Sometimes they even go to 0 at infinity. For that reason, if we want to have eigenfunctions, have resonances, or I call them eigenfunctions, with which we can expand a physical field, it is very useful to have such resonances or such eigenstates that also never diverge.
Yes.
Now, in the case of simple structures where you have only two constituents, which is what I treated and discussed in my lecture last week, there are scattering eigenstates that are always finite. In fact, they go to 0 when you go to infinity. And they are always normalizable. You don't have to do any mathematical tricks to normalize them. And when you use them to expand the physical field, of course, the eigenstates are finite, and the physical field also comes out finite. The only cases where things diverge is if the system, the physical parameters are close to those of an eigenstate. And that, of course, they can never be exactly equal to those of an eigenstate. But if you get close to an eigenstate, if they are close to those of an eigenstate, then the physical field also becomes very, very large. But that's then exactly what you expect. If you do an experiment where the system is close to an eigenstate, or the system parameters are close to the eigenvalues, then of course you expect that the system response will become stronger and stronger. Now, I did this only for two constituent systems, but I'm sure that this can be generalized to multi-component systems, which I will do shortly. I've already started doing it. So I just wanted to point out, as I said, that it is not absolutely necessary to have resonances or eigenstates that diverge.
Yeah, yeah. I agree with everything you say. The market for the sort of results I've been describing is to actually novel methods for approaching these problems, and might be worried by this apparent divergence. Since it was possible to treat the divergence head on, that was what I did. But this, of course, doesn't preclude any other alternate approaches. In fact, I very much like expansions in terms of these resonant states. In terms of the physics of what goes on, there's also a problem which has worried me for a long time, which is that one has parameters epsilon and mu, and if one is thinking in terms of complex frequency or complex wave number, one would like to be able to plug in values for epsilon and mu, but of course experiments most often are carried out at specified real frequencies, and therefore extrapolation procedures into the complex plane are necessary, which adds to the difficulties of the problem, conceptually as well as physically.
Actually, sorry, go on.
Yeah, so, you know, I've been dealing with these sort of problems for a long time, and the imprecision of experimental measurements has been a long-term fly in the ointment.
What I was starting to say before is that actually the eigenstates that I'm talking about and that I described last week, the eigenvalues are not special values of the frequency. The eigenvalues are special values of the physical parameters, like epsilon, mu, sigma, the conductivity. The frequency is always real, and therefore there's no problem. You can use experimental values for these parameters, for epsilon and mu, and they are usually complex, but they depend, if the frequency is known, they depend on a real frequency, which is also a known parameters.
Yep. Yep. If you're dealing with time-dependent problems, that becomes, again, if you're dealing with time-dependent problems, you'll inevitably, I think, have a complex frequency. And that, again, is very interesting. The market, as I said, was saying for the results I've been describing, may well be more substantial in applied mathematics than in physics, but I really don't know. My attitude was to try and actually apply results derived in another context to give people at least analytic expressions for these integrals. If they were determined to do it using PMLs or something like that, at least they could have access to more accurate test results.
Okay, thank you.
Yes.
Hi, Ross. Thank you for the nice talk. I like the slide where you summarize the textbooks on special functions. Can you walk us again over that slide? And I was surprised that there is a book which is more complete, or at least I think you like it more than Morse and Feshbach.
Well, the book I like most for special functions, actually, apart from the Handbook of Mathematical Functions and its successor, Whittaker and Watson's book on complex variable theory, I find is very good. It's Cambridge University Press. No?
And I see,
okay.
I see number 6. So you'll
6. I like Jones because I've been working a long time on electromagnetism, and Jones has a very strong background in electromagnetism. So he wrote a very substantial book on electromagnetic theory, and he also wrote an influential book on, well, I find it very useful, on generalized functions. If you're coming to generalized functions for the first time, the classic route is to use Lighthill's book, which is a fantastic introduction. It's about 70 or 80 pages, very concise and very useful. But if you want to go beyond that, you can go to which, as I said, there's a second edition which is still available. And that, for example, gives you generalized functions and their relationship to Bessel functions and the like. So it's very useful for scattering problems. Also gives you results. Some people like to use fractional calculus. You get the same results using generalized functions.
It's interesting.
Yeah. It's as I said, perhaps generalized functions aren't as fashionable as they used to be, but if you've got a book like Jones, you'll find plenty of useful results.
Thank you.
Thank you, Emil.
So also maybe a follow-up. Can you summarize, so what were the geometries that you can approach with this? So it's the sphere, but you also mentioned the cylinder.
Yeah.
So this are the two.
So yes, I've done a lot of work on microstructured optical fibers. There you have a collection of, I don't know, several hundred cylindrical scatterers. And you want to know to high accuracy the propagation constants of waves passing along, guided by the cylinders along a central core. We have used multipole methods for that sort of problem. In those cases, we put a jacket at infinity or at large radius to confine the problem, but with this approach, you don't need that. So yeah, that's the sort of photonic clusters in general. Or photonic crystal is a periodic system. Photonic cluster is typically a finite subset of an infinite periodic system.
But then you need to apply graph addition theorem. You can apply a graph addition theorem to your very special functions.
Yes. If you're dealing with multiple cylinders, then you use or spheres, you'll use the addition theorem to go from internal expansions between the cylinders or spheres to an external expansion with a single origin, which will be at the center of the a sphere at infinity, or which approaches infinity, and the result will be that you can neglect the flux at infinity in your treatment of any complex modes. So that would be a sort of T-matrix technique for solving such a problem. They can be highly accurate. These techniques. The case of microstructure fibers, people were interested in knowing imaginary parts of propagation constants around 10 to the minus 10 compared with the real parts. And multipole methods gave that quite readily.
And you mentioned you made some comparisons with other techniques. Hugonant, you mentioned perhaps you made some comparisons with what, for instance, people like Philippe Lalanne or André Nicolet, Frédéric Zola are doing.
Yeah, Philippe writes papers essentially using Hugonant's code. The most accurate results come out of Hugonant's code, and so that was 5 or 6 decimals of agreement, which is probably as much as is needed in most practical cases. From long experience, I'm never quite satisfied with 3 decimal places of stability. I always need a couple more figures than that, but you'll find in conventional literature people don't often quote precise numerical values. They tend to give graphical results more than precise numerics, which hinders one in actually comparing new techniques with existing techniques.
Do we have any more questions? The range of subjects can be well beyond what Ross discussed today. Yeah. Feel free to... Yes?
I just wanted to thank Ross for a very interesting talk.
Thank you, David.
Thank you very much.
Thank you.
Okay, so thanks a lot, Ross. By the way, did you make any new discoveries regarding, this, Riemann zeta function?
I'm still having fun with that.
Yeah, so I've seen that. And any way to connect this to the talk of today? No?
Not that I know of, but certainly integral representations of the zeta function are very useful. So maybe some of the tricks that I've described might be useful in that case. But yeah, it's a very interesting and difficult problem.
thanks again for this really inspirational talk. And please, people, do not hesitate to drop an email to Ross if you have any question. I'm sure he will be very pleased to interact with you. And, in the meantime, let's thank our speaker again for this fantastic talk.
Thank you.
Don't get a good night's sleep now.
Yeah, and I can go to sleep. Provided the dog doesn't wake me up. See you later.
Let's see, Sebastian and Bogdan, can you give us an update on the workshop, the MetaMAT's workshop?
Sure. Bogdan, please, go ahead.